Okay, this is section 10.4, guys. This is the last section. It's called Analysis of Variance, One-Way ANOVA. ANOVA stands for Analysis of Variance. And let me show you, and the good news is we're gonna be using technology. Otherwise, it's a lot of tedious work, just to do this section. So let me give you an example. Suppose a medical researcher is analyzing the effectiveness of 3 types of pain relievers and wants to determine whether there is a difference in the mean length of time it takes the 3 medications to provide relief. So you can see here, when you want to compare 2 means, you learned that already in chapter 8. You do mu1 and mu2. But what about if you have 3 means? What can we do? All the tools that you acquired in chapter 8 will not work because it has more than 2. So there must be a tool that would allow us to compare means beyond 2 of them. And here you read in the example, it says 3 medication. So what we can use, guys, is a distribution called an F distribution. So far you learned Z distribution, you learned T distribution, you learned chi-square distribution, and now you're gonna learn the last one, which is F distribution, but we will be using the calculator to demonstrate this. So there will be no work on your side where you have to crunch, the test statistic by hand. We'll just use technology. And I will show you the F distribution in a second. So we'll be using the F distribution with a technique called analysis of variance. Because one independent variable is being studied, the process is called one-way analysis of variance. So what is one-way analysis of variance, guys? It's a hypothesis testing technique that's used to compare the means of 3 or more population. And it is abbreviated by ANOVA. And to show you the ANOVA test, guys, it's the last test on your calculator. Just watch. Second and quit. I'm gonna go to stat. I wanna show you the test. It's the last one. Here you go. That's the last test. It's very easy test to use. You will see. Just bear with me for a few minutes. Okay. Here is what we can do with this test, which is called ANOVA, analysis of variance. We can compare if 3 or more means are equal or if one mean is different from the others. So this is the only thing that we can do with this test, to check if they are equal or not. And look what the statement is for the null and the alternative hypothesis. So the first step in a one-way analysis of variance is to state the null and the alternative hypothesis. And guys, this is the only way you state the null and the alternative hypothesis. You state for HO, you state mu1 equals mu2 equals mu3 equals mu4, etc. If he gives you 3 sets, you stop here. If he gives you 4 sets, you add equals mu4. If he gives you 5 sets, you add equals mu5. And for the alternative hypothesis, you have to memorize this, guys. You're right, at least one mean is different from the others. This is the statement that you make in every single problem. Any questions so far? These are the conditions of the test, which don't worry about. When we ask you to do it, then the conditions are met. Each sample must be randomly selected from a normal or approximately normal population. See how important the samples to be random. The samples must be independent of each other. So one mean comes from a sample, the other mean comes from a different sample that they are not related at all. And each population must have the same variance. These are the 3 conditions of the test. So each sample is randomly selected from a normal population. Samples are independent, and each population must have the same variance. So all the population have the same variation. Now let me show you the F distribution, guys, and then I'll give you an example and show you how to do those problems. Okay, this is the F distribution. It involves two sets. The test statistic for the F distribution is S1 squared divided by S2 squared. Sample variance of two different populations, both population and normal population variance sigma 1 and sigma are equal, then the sampling distribution is given by this. Don't worry about this. All I wanted to see how the F distribution looks like. Okay. The F distribution is not only one curve, it's a family of curves. It changes with the degrees of freedom. We have 2 degrees of freedom. One is called degrees of freedom of numerator for the top, and one is called degrees of freedom of denominator. The F distribution is positively skewed, means it's skewed to the right, guys, and it is positive, starts at 0, as you can see. Total area under the curve is always 100%. All the values of F are greater than or equal to 0. You cannot have anything negative in the F distribution. For all F distribution, the mean value of F is approximately equal to 1. And you notice, guys, as you increase the degrees of freedom, it will become closer and closer to a normal distribution. Look how skewed it is when the degrees of freedom are small. But when you go higher and higher and higher, it will become like a bell-shaped curve. So this is what the F distribution for different degrees of freedom. We will be using this, and your test statistic now will be called F. So you guys, you worked with Z, you work with T, you work with chi-square, and in section 10.4, it's gonna be F equals when you compute the test statistic. And I think, guys, I'm ready to show you how to do a question, and you're gonna see how straightforward it is to use this test. So this is called analysis of variance test, and it's abbreviated by ANOVA. So let me select an exercise, couple exercises, guys, and show you how to do that. So have your calculator handy because I like you to work with me on this. So let's read the question, guys. Number 6. The table shows the prices in dollars for a sample of automobile batteries. The prices are classified according to battery type. At alpha equals 5%, is there enough evidence to conclude at least one mean battery price is different from the others? So he's given us, did you notice, guys, that there are 3 sets here, not 2, because ANOVA is for 3 or more. And he's asking us to check if at least one mean battery price is different from the others. This is called an ANOVA test. And I'm gonna show you guys, and he says that alpha equals 5%. Is there enough evidence to conclude that at least one mean battery price is different from the others? So let me walk you through the steps. Page 565, number 6. And watch, guys. Look what you put. Step 1. HO. How many means do we have, guys, involved in this one? Can someone tell me by replying to the chat? 3. Look what you write. mu1 equals mu2 equals mu3. And then HA. At least one mean is different from the others. You can memorize this, guys. It's always the same statement. And this is my claim. He says, can you conclude that one mean is different from the others? All right, and that's all I have to do by hand. Now watch the calculator performing the work. I'm not gonna do the critical value approach for this. It's just a p-value. And you guys, you're gonna like how straightforward this. Tests. So you go to tests. And then scroll up. It's ANOVA. Any guess, guys? What should I enter there? You should be able to guess it. What do I put in there? L1, L2, L3, exactly, and put a comma in between. So second, number 1, Don't forget the comma, guys. Comma. Second. Number 2. Comma. Second. Number 3. Close. So ANOVA, L1, L2, L3. And then I'm gonna hit enter, guys, and I'm done. You see, the first value is the test statistic F, and the second value is the p-value. I'm just gonna write them down. Any questions? Oh, the comma is right above 7, number 7. Okay, so I'll write down what I got, guys. So you do ANOVA, L1, L2, L3. F is 2 decimal places, usually. P-value, as we've been doing, 4 decimal places. And I'm done with the calculator. I no longer need it, which is more than alpha, guys. He gave us alpha to be 5%. You failed to reject HO. And here's the conclusion. There is not enough evidence at the 0.05 level of significance to conclude that at least one mean is different from the others. I'm just copying the statement. So probably the 3 batteries cost the same on average. Any questions, guys? We're gonna do one more. So let's read that question. In a recent study, a health insurance company investigated the number of days patients spent at the hospital. In part of the study, the company selected a sample of patients from 4 regions of the United States and recorded the number of days each patient spent at the hospital. The table shows the results of the study at alpha equal 1%. Can the company reject the claim? So it's either your answer is going to be yes, I can reject the claim, or no, I can't reject the claim. That the mean number of days patients spend at the hospital is the same for all 4 regions. Okay, let's write it down, guys, and show you how to do this. Number 12. How many means do I write here, guys? There are 4 sets, so it's 4 means. And at least one mean is different from the others. See, I am consistent here. I'm not changing anything. Where is the claim here? Is it an HO or a HA? In the null hypothesis or the alternative hypothesis? Yes, it is in the null hypothesis, because he says, can you reject the claim that they are the same? So this is the claim. Okay, guys, you're gonna go to ANOVA and you're gonna enter L1, L2, L3, and L4. So let's do this. And just for your information, he says here at the very beginning of the page that assume that the samples are randomly and independent, the population are normal distribution, and the population variances are equal. If convenience, use technology. So he's telling you all the conditions of the test are met. Okay, guys, so we're gonna quit here. You're gonna go to stat. And you're gonna go to tests, scroll up, ANOVA. ANOVA stands for analysis of variance, one-way analysis of variance. Okay, input L1, comma, input L2, comma, input L3, comma, input L4, comma, and that's enter. And here you go. I got PF to be 0.56 and P value, guys, I got 0.6476, which is more than alpha. Failed to reject the null hypothesis. In my conclusion, he says, can you reject the claim? I say no, because the claim happened to be in the null hypothesis and I cannot reject the null hypothesis. So there is not enough evidence at, what is alpha here? At the 0.01 level of significance to reject the claim. I'm just going to copy it and paste it. That the mean number of days patients spend at the hospital is the same for all regions. That the mean number of days patients spent at the hospital is the same for all regions. That concludes this section, guys. So now the test for review, as I told you, will cover 2 chapters, correlation and regression, and chi-square tests. The first question, given the size of a human brain X and the score on an IQ test Y, would you expect a positive correlation, a negative correlation, or no correlation? This is just a general question. Don't worry too much about it. You guys, there is no relationship between the size of someone's head or brain and how smart they are. There's no research that says that there is a relationship. But so here it just say no correlation, no relationship. Okay. What I'm gonna do, I'm gonna skip 2 and just do 3 because they are all very much the same when it comes to entering data. So what I like you to do, guys, for number 2, I'm just asking you to do a scatter plot. What I'm gonna do the scatter plot in number 3. So then I will answer 2 at the same time. So I will pause for a minute and have you enter the data in L1 and L2 for number 3. Okay, scatter plot. Do we still remember how to do scatter plot? First of all, make sure that your stat plot is turned on. So watch. So second, y equals, enter. Make sure this is on. This is selected L1, L2. So mine, yeah, is ready. So I'm gonna quit. And you just go to zoom and then number 9. There you go. This is the data set. So I might give you a question, scatter plot of the data set, and then give you 4 graphs. So you do it in your calculator, try to match it with the graph that you see on the screen. This is how you do the scatter plot. The second question, guys, is to find the correlation coefficient R. Okay, how do you do that? So you go to stat, calc, number 4, enter, L1, L2, I'll put everything in L1 and L2, calculate, and R is 0.632. And then I'm asking you to find R squared. Well, R squared is already displayed for you. It's 0.39. Well, let's do it. If we do it to 2 decimal places, it will be 0.40. Then I'm asking you in number 3 to interpret the value of r squared. Let me again tell you how to interpret the value. Change it to a percent, which is 40%. And here's what you write. 40% of the variation in sales can be explained by the variation in miles traveled using the regression line. Okay, guys, so that answers number 3. But I'm gonna add one more question to number 3. Let's find the equation of the regression line. So you get y equals ax plus b. When you run a linear regression ax plus b, you get the value of r, you get r squared. Look, guys, at the screen, and you get the equation of the line, which is called y hat equals ax plus b. Now, Muhammad is asking me, how do I see the line? Here's how you see the line. Watch. You go to y equals right here, and then you enter the equation. 3.53, and you want to see where x is right here, right here. So x plus 34.86, and then graph. There you go. This is the line. So we're gonna do number 4. I would like you to input the data for temperature in L1 and the data for number of absences in L2. Okay, now guys, watch. Stat, calc, number 4. Press enter. If you don't see this window, press enter again. But if you see it, guys, make sure your X list is L1, your Y list is L2, your frequency list is empty. Nothing here. And then hit calculate. And I'm gonna write down the values. R is 0.98. R squared is negative, 0.96. And the equation is 0.45x minus 26.82. So see, we answered 3 questions here, but we still haven't answered what he wants us to do in number 4. There you go, guys. This is the output. This. If he asks you to comment on the relationship, well, since R is very close to 1, guys, you say there appears to be a strong, very strong, positive linear relationship between the temperature and the number of absences. If he asks you to find the equation of the regression line, well, we already found the equation of the regression line. It's y equals 0.45x minus 26.82. If he asks you to find the number of absences when the temperature is 92, what do you do, guys, when the temperature is 92? You just plug in x equals 92 in here, and then you find the number of absences. If he asks you to comment, find the coefficient of determination R squared and comment on the relationship. Here's how you do it. R square is 0.96. You say 96% of the variation in the number of absences can be explained by the variation in temperature using the regression line. So this is everything we learn now. The last one that we haven't done is test the significance of the correlation rho equals 0 and rho not equal to 0. So I'm going to do this on the side, and we're going to use technology here to do it. So for number 4. Okay. He says test that rho equals 0, and then you know the opposite of that will be not equal 0. Here you're right, correlation is significant. And here you put correlation not significant, always. And what's the name, the test that we run, guys? Linear regression t-test. So I'm gonna go ahead and run that test for you. Watch. Stat, tests, scroll up, and it's F, guys, right here. I'll just move it a little bit here. Enter. L1 is good. L2, good. Frequency, don't touch this. Equal or not equal, we're testing. He didn't say positive, negative. That's why we did equal or not equal. If he says positive, we would do positive. If he says negative correlation, we'd do negative. But he says not equal to 0. Equal or not equal to 0, and then calculate. T is 13.031. P-value. Do you guys see the E minus 6? Please don't ignore that. That means you have to move the decimal 6 digits to the left. So your p-value is 0, guys, which is less than alpha. Reject HO. When you reject HO, you conclude that correlation is significant. Remember that there is enough evidence at the 0.02 level of significance. This is the first time they give us 0.02 to conclude that correlation is significant between temperature and number of days being absent. All right, so that is number 4, guys. A random sample of 160 car crashes are selected and categorized by age. The results are listed below. The age distribution of drivers for the given category is 18% for the under 26, 39% for 26 to 45 years old, 31% for 45 to 65, and 12% for over 65. Test the claim that all ages have crash rates proportional to their driving rates. Okay, this is a goodness of fit test. Okay, here's how you begin, guys. Distribution of driving age rates is as claimed. And here, distribution of driving age rates has changed. And here, this is where the claim, he said, test the claim that it is still the same proportion. Okay, I'm gonna do this one using technology, first of all, and the test, guys, as I told you, it is chi-square goodness of fit test. But in order to use this test, you need to provide the O's and the E's. These are the O's. Let's find the E's together, guys. Can someone tell me what would be the ease for under 26? We know the observed values are 66. What would it be for the expected frequency? You know the total is 160. And what's the percent for drivers who are under 26? It's what? 18%. So you do, guys, 0.18 times 160. What is that? Okay, I got 28.8. I'm just gonna round it to 29. Next one, 39. What would that be for ages 26 to 45, guys? It's 39%. So you're gonna do 0.39 times 160. And let's do this. 62.4, I'm just gonna leave it as 62. You know what, I'll just do 62.4 and 28.8 since we're using technology, so it doesn't really matter. Okay, for ages 46 to 65, if you're wondering where I'm getting the percents are from here, guys. 31% now, which is 0.31 times 160. And this is 0.31 times 160. I got 49.6, guys. And we got one more, the last one. The last one is 12%. And 12% of 160, 0.12 times 160, 19.2. Okay, these are the E's. And now I'm gonna go slowly and show you how to use the calculator. So I'm gonna go to Stat, Edit. I'm gonna clear L1. Look how do I clear L1. I select it and hit clear right here and then enter. I'm gonna clear L2. Oh, I didn't hit clear. Select L2, sorry. Stat, Edit. And then select L2, clear, enter. Okay, observe values. 66. Oops, sorry. Should be here. 66, 39, 25, and 30. Now, expected values. I got 28.8. I got 62.4. I got 49.6. And I got 19.2. Any questions so far? Okay. And now, guys, go to Stat, Tests, scroll up. It's this test, goodness of fit test. Enter. L1, L2, degrees of freedom. It's number of categories minus 1. I got, guys, 1, 2, 3, 4 categories minus 1. It's a 3. So I have to put 3 here. And then hit calculate. So I got chi-square to be 75.101. And the p-value is almost 0. You can see E minus 16, so it is a 0. So let me do that. So chi-square GOF test. Chi-square is 75.101. P-value is 0. Don't disregard the negative 16, guys. It means you have to move the decimal point 16 digits. This is less than alpha. We reject the null hypothesis. And then we say there is enough evidence to reject the claim that distribution of driving age rates is as claimed above. At the 5% level of significance. Oh, he didn't give us alpha, well, 5%. It doesn't matter what alpha is, guys, because the p-value is 0. No matter what alpha is, you're going to reject the null hypothesis. So this is a review for section 10.1. Now, how do you find the test statistic, guys? You just add them up. So you get 1369 divided by 29. Add up the last column. Plus 529 divided by 62. Plus 625 divided by 50. Plus 121 divided by 19. I should get something close to 75. It's not going to be as accurate as the calculator. Now, if you guys on the test, I don't tell you which method to do, feel free to use the p-value. It's up to you. So I'm doing the work now. I'm going to put them in the calculator and show you what the answer is going to be, guys. Okay, I got this. Watch. I got 74.6, which is very close to what we got on the calculator. Because we round it here, so the answer is slightly different. Now, to test this one, you use the critical value approach. We should reject HO definitely, guys. If we don't, that means we have a contradiction here. We did reject HO. You bring this table, chi-square table. Degrees of freedom, I have 4 categories. -1 is 3, and we're gonna use alpha is 5%. So watch, guys. 3 right here and 5% right there. So I got 7.815. And your test statistic is about 75, guys. So it's going to be way to the right. So you reject what? HO, and you get the same results as we did with the calculator. All right. Be sure to do the following. Identify the claim, state the null and the alternative hypotheses. Okay, you don't have to find the critical value. We're going to use the p-value here. Calculate the test statistic, decide to reject or fail to reject the null hypothesis, interpret the decision in the context of the original claim. Okay, guys, I'm going to show you one more time how to do this one using technology. We have to enter this and put it into a matrix. Remember that. And if you forget, you can go back to this video or other videos and play the last 10 minutes of this video. First of all, let's put the null and the alternative hypothesis. So this is about opinion and pari. The contingency table shows the pari and opinion on a bill of a random sample of 200 state representatives. Okay. The question is, which I did not write there, we wanted to test the claim that opinion on a bill and the pari are related. So test the claim that opinion on a bill and affiliated pari are related. Use alpha equals 0.05. I'll write it down right here, guys. That's number 7. So test the claim that opinion on a bill and affiliated party are related, are dependent. So your HO will be opinion on a bill and party are independent. Always independent in HO. And here, opinion on a bill and affiliated party are dependent or related. And this is my claim. You're ready, guys, for the fun part, how to find the test statistic. Okay, you will be able to use technology, so please watch me doing this. I have 3 rows of data and I have 3 columns of data. So watch. Quit the screen, nice and clean screen, and then I'll walk you through the steps. You can do it with me, guys. So right here, I'll make sure that you can see everything that we're gonna do. Okay, you press second and matrix right here, guys. And then you go to edit. And then you press enter. My matrix is 3 by 3. So you type 3, enter, and then 3 again. And then you key in the data entries as you see them right here. Exactly as you see them. Look, I start with 42, enter. Then I do 20. Then I do 14. And then I go to the next line, I do 50, 24, 18, 10, 16, and 6. Yes? That's a very important step, guys, that you know how to do that if you want to use technology. You have to be able to enter the observed values, put them into a matrix. And don't worry about the expected. They will come to you automatically. Now, we run a test. So this goes into a matrix first. Now we run a test called chi-square test. Okay, here's how you run the test. You go to stat, tests, chi-square, enter. Okay, are your observed values in A? They are. The expected values, the calculator are gonna put them in B and then hit calculate. So chi-square equals 8.030 and p-value is 0.0905. Okay, I'm done here. For the degrees of freedom, guys, if you wonder how did the calculator pick it up as 4, it's number of rows minus 1 times number of columns minus 1. I have 3 rows, minus 1 will be 2. I have 3 columns, minus 1 will be 2. 2 times 2 is 4. Okay, and now this is bigger than alpha. I say that 5%. So fail to reject HO. If the answers in the back that I provided, guys, don't match, please disregard them because I'm using probably different alphas or different stuff. Just follow my solution here. So we fail to reject HO, and then we cannot support the claim. So we say there is not enough evidence at the 5% level of significance to conclude that opinion, or to support the claim if you want, to conclude that opinion in a bill and the pari are dependent. We cannot say that they are dependent. We cannot support this claim. And that concludes this question, guys. Now, what I might give you a question on the test just to find the expected values. I'm going to show you how to find the expected values without doing any work. You already did the test, so let me show you how to retrieve the expected value. They are in a matrix called B. Watch, guys. So let me clear the screen. Second and clear. You go to second, watch. It's really neat here. Second and matrix. Okay, go to B. Press enter. Press enter again. And here you go. These are your expected values. 38.76, 22.8, 14.44. So you have 9 observed values. You should get 9 expected frequencies, and they are given to you in here. So this is about section 10.2. Now I'm going to go to the last one, which is section 10.4, which just did this morning. Researcher, which is ANOVA. A researcher wishes to compare time it takes workers to assemble a certain computer component using different machines. Workers are randomly selected, randomly assigned to one of 3 different machines. The time in minutes it takes each worker to assemble the components is recorded. Test the claim that there is no difference in the mean assembly times for the 3 machines. What does no difference, guys, means? No difference means they are all equal. So that's what we need to check. So HO, how many means? I got 3 of them. HA, I do not change this one. At least one of the means is different from the others. This is the claim. Again, guys, if you ask me why I put the claim in HO, because it says there is no difference. No difference means equal. When I say there's no difference between what I make and what you make an hour, that means we make an equal amount. And that's what it means here. Okay, so guys, I'm gonna give you a minute to put this in L1, L2, L3, and then we will continue after a couple minutes. Okay, so let's back on. So we input machine 1, machine 2, machine 3 in L1, L2, L3, and we run ANOVA stat tests, ANOVA, and make sure, guys, you do second and number 1 with a comma, second with number 2 with a comma, and then second with number 3 and close parentheses, and enter. So ANOVA, L1, L2, L3. F is 7.103. P-value is 0.0074. And what did he say here? At alpha equals 0.01. This is less, guys, than 0.01. And because it is less than 0.01, I'll move up. I know. You reject the null hypothesis. And then you reject the claim. So there is enough evidence at the 0.01 level of significance to reject the claim that there is no difference in the mean assembly time. So that means there is a difference actually. for the three machines. All right, guys, so that concludes the review.